In this video, I want to lay out the search intuition, the basic idea that's going to underlie our Sudoku board solver. As I said before, the basic idea is we're going to take an initial Sudoku board and we're going to generate a tree of all the possible boards that follow from it, looking for a solution. Now that may seem surprising. When you look at a Sudoku board on paper, it doesn't look like a tree. And as we saw, our representation of the board is just a single flat list, so there's no tree there. So where's the tree? Well, we're going to generate the tree. It's going to be a generative recursion. Here we go. Imagine that you start with a board, and here I'm just kind of showing the upper left part of the board. So imagine that you start with a board that has some squares filled in, kind of like a Sudoku puzzle you might see in the newspaper. You may remember newspapers are things printed on paper that come to your doorstep in the morning. So you might see it on your phone or something. But here is the upper left part of a Sudoku puzzle. So you want to find a solution to that problem. Or maybe find out that the board's not solvable. What could you do? Well, the idea behind brute force search is, here's the first empty square. That's the first place where there's not a number. What if I take that square and I fill it in with all possible values? That gives me 9 possible next boards, because I basically fill the empty square with 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, of course, some of those boards are immediately invalid, right? The second board is invalid because that gives you 2 2s in the same row. So we can cross that one out right away. And the third board is invalid because it gives you 2 4s in the same row. And the fifth board is invalid because it gives you 2 5s in the same box. So we can kind of immediately rule out the invalid boards. And in this case, that leaves us with just 6 next boards. So now what do we do? Well, none of those boards is a complete solution, right? Because none of those boards has no empty spaces. Right? Then we just do the same thing again. We find the next empty square. We fill it in with the 9 possible values, and we prune. Now we've got some more empty boards. And what's going on here? What are we doing? What I want to say to you is that there's 3 crucial aspects to what's going on here. We are generating an arbitrary arity tree, and we're doing a backtracking search over it. Those are the 3 things. Let me explain them in turn. First, the generation. Well, the generation is straightforward. This second row of boards here, those are new boards. Those boards aren't some subpart of the first board. We didn't take the rest of the first board to get those boards. The rest of the first board is just a list 80 elements long. We had to generate these new boards. So that's why this is generation. And because it's generation, you could start to think, generative recursion. Generative recursion template probably plays along in here. Now, arbitrary arity, the reason I'm saying it's an arbitrary arity tree is that each board has 0 to 9 valid children, 0 to 9 valid next boards. Okay? Because for each board, we take the first empty square, we fill it in with the 9 possible values, 1 to 9, and then we prune the invalid ones. So there could be up to 9 valid children. That's why it's an arbitrary arity tree. And we're doing a backtracking search over it. Well, the reason we're doing a backtracking search is just we're going to keep exploring this tree until we come to a board that has no valid next boards. That's a board with no children. And what do we usually do when we're searching for something and we wind up nowhere? And we produce false. That's the idea of backtracking. When you get to looking for something in nothing, you're in trouble. So you produce false. Or we're going to come to a board that's full. Now, because of the way we're producing the tree, because of the way we're generating a tree, where we immediately throw out invalid boards, if we come to a board that's full, then it's a solution. Because we only add valid boards to the tree. We immediately throw out invalid boards. So if we come to a full board, we know it's valid, that's the solution, yay, we produce that. So we're going to generate the tree and keep walking down the branches, sometimes backtracking by producing false, and hopefully at some point finding the answer we want. So the key thing to take away from this idea of the search intuition is, in our terminology, in what we understand from systematic program design, if somebody says, hey, this is the thing I want you to do, we say, oh yeah, that has three crucial aspects. It's a generative recursion, it's a recursion over an arbitrary arity tree, and actually we're doing backtracking search over it. Now what I'll say to you is, you know how to do those three things already. In the next video, I'm going to show you how to combine them, and then the hard part of Sudoku is done.